All right, so we're going to prove some remaining facts about polynomials, a couple, to close out the chapter. So the first fact is something you usually see in rings and fields at Casa San Bernardino. I'm going to not do the proof in the book of the remainder theorem. We're going to do the standard proof that you see, but there is a separate proof in the book. Okay, so let P of t be a polynomial. Really, it doesn't. It can be in some subfield K of C. K subset C is a subfield. It doesn't matter if it's C or a subfield. Same is true. Then for any alpha in C, this is an alpha. Firstly, there exists some Q of T in C adjoin T. Dang, I keep messing up in K adjoin T, sorry. Keep messing this up. Such that P of T is T minus alpha, Q of T plus R. And secondly, R is Q of alpha in 1, or P of alpha rather, in 1. Now what is this saying? It's not saying anything smart. It's saying that the whole theorem is saying that when you divide P of t by t minus alpha, you get some quotient Q of t and some remainder R. And what is R? Well, R is what happens when you plug alpha into P. That's all it's saying. The proof of this is just the division algorithm. Well, let me say it better. By the division algorithm, which applies because we have a field. K is a subfield of C. Wouldn't necessarily apply if we had a subring, but we have a subfield. By the division algorithm, there is actually unique Q of t and R of t in K adjoin T, such that P of t is t minus alpha Q of t plus R of t. Let me fix that Q. And the degree of R is less than the degree of P. Of t minus alpha, rather, not P. Oops. T minus alpha. The degree of t minus alpha is 1. So that is to say, R is a constant. So that's the proof of 1. We did it. In fact, we proved more. Q of t is actually unique. For 2, we can plug in alpha. And let's note that since R is a constant, R of alpha is just some constant R that we don't know. To get, well, on the one hand, we have P of alpha. That's plugging in alpha to the left-hand side. On the right-hand side, when we plug in alpha, we get alpha minus alpha Q of alpha plus R. But alpha minus alpha is 0. And so we just get R because the Q of alpha gets zeroed out. But that's the second part, right? It's that R should be P of alpha. Okay, so fine. The remainder theorem is very helpful. It tells you that when you divide a polynomial by a linear expression, a monic linear expression, degree 1, the leading coefficient is 1 here. This t minus alpha has leading coefficient 1. Then you have some remainder, and the remainder is the value of the function at that point. Okay. Ooh, hang on 1 second. There we go. Sorry, I pushed something. And then we have an immediate corollary of this. Corollary. The complex number alpha is a 0 of P if there exists Q of T such that P of T is T minus alpha times Q of T. And this is obvious. There's nothing to prove here. If P of alpha is 0, then the R is 0 from before. And so you just get T minus alpha as a factor. So what this is telling us is that a fact that you probably know already, but zeros correspond to linear factors. Obviously, if you can pull out a linear factor, it must be a zero. And conversely, if you have a zero, it corresponds to linear factors. And then we're going to end this video and the chapter with a proposition, which is often how the fundamental theorem of algebra is actually stated. And the proposition is this. So suppose we have a polynomial with coefficients in, this is going to be honestly c here. And the degree of p is at least 1, then there exist complex numbers in C, and some non-zero k in C, such that P of t factors completely into a product of linear factors. Moreover, k is just the leading coefficient of P. Of course, what else would it be? It's the thing that will end up being the leading coefficient. All right, proof. Proof of this is simple. We proceed by induction. If n is equal to 1, then P is linear. And we can write this as A times T minus negative B over A, where A is not 0 because it has degree 1, so the leading coefficient has to be non-zero. Okay, if n is bigger than 1, by the fundamental theorem of algebra, there exists some alpha, I'm going to call it alpha n in C, such that P of alpha n is 0. Then T minus alpha n is a factor of P. Well, why? Because we have a 0. So there exists some Q of T of degree 1 less, such that P of T is T minus alpha n times Q of T. Why is it degree 1 less? Well, the degrees have to sum to the degree of P, which is n, and T minus alpha n has degree 1. So this must be 1 less than n, so that they add up to n. By the induction, since Q has degree n minus 1, Q of T factors entirely as a product for some alpha 1 to alpha n minus 1 in C, and k not 0 in C. The k is, of course, just the leading coefficient of Q, and since the leading coefficient of T minus alpha n is 1, that will also be the leading coefficient of P. Thus, P of T admits a complete factoring as k is Q times T minus alpha n. So here's our Q part, and then here's our T minus alpha n part. That's it. And this is another way of stating the fundamental theorem of algebra. It's equivalent to it. Let me point out one thing here. The proof of this is simple. It's what we always do. You pull out a linear factor, and then you pull out another linear factor, and then you pull out another linear factor. That's all that's going on here. So what we've learned here is that every polynomial factors completely over C. Into a product, every non-constant polynomial factors completely into a product of linear factors. And let me say one last thing here, a definition. If alpha is a root of P, then the multiplicity of alpha, root or 0, however you want to call it, the multiplicity of alpha is the natural number m it's a root, so m is going to be at least 1, such that t minus alpha to the m is a factor of p of t, but the next one is not a factor. So t minus alpha to m plus 1 is not a factor of p of t. That's called the multiplicity. And all this is saying is, well, factor p entirely, and then count how many times you see t minus alpha in the factor. So just a quick example. If we had the polynomial t minus 1, t minus 2 squared, t minus 3 cubed, well, 1 is a 0. It's called a simple 0 because the multiplicity is 1. So we refer to those as simple zeros. 2 is a 0 of multiplicity 2. Let me change the powers, actually. Let's go 3, 2, so that it's not super. Let's go 3, 4. 2 is a 0 of multiplicity 3, and 3 is a 0 of multiplicity 4. It's just how many times the t minus whatever shows up. All right, and that concludes chapter 2.